Welcome to our deep dive today. We're going to be looking at something pretty fascinating, the connection between graph theory and number theory.
Oh, that sounds interesting.
It is. And specifically, we'll be focusing on sign trees and how they connect to a certain integer sequence, A000606 from the Online Encyclopedia of Integer Sequences. You probably know it as OEIS.
Ah, yes, the OEIS, a treasure trove for number theory enthusiasts.
Definitely. It's like a giant database cataloging all these integer sequences, each with its own unique story.
I've always thought of it as a fingerprint database. You know, for math patterns, you search a sequence, uncover its properties, see how it connects to others, and maybe even discover some applications in unexpected fields.
Precisely. And today, the sequence that's caught our attention is A00000000. It might seem deceptively simple, but it enumerates the number of signed trees you can create given a specific number of nodes. But before we jump into the sequence itself, I think we should probably clarify what exactly we mean by a signed tree.
Right, good point. So, in the world of graph theory, you have your typical tree, nodes connected by edges, forming a structure with no cycles. Now imagine adding a plus or minus sign to each of those edges. That's essentially what we're doing when we talk about signing a tree. We're basically adding a whole new layer of complexity to the structure.
So we're taking a familiar concept from graph theory and spicing things up a bit, adding a mathematical twist. How does this tie in with our integer sequence, A000006?
Well, A000006 gives us the count, the number of distinct signed trees we can build with a specific number of nodes. To give you an example, the first few terms in the sequence are 1, 2, 3, 10, 27, and so on.
Okay, let's break that down a bit. So the fourth term, 10. That means there are 10 different ways to create a signed tree with 4 nodes.
Exactly. You start to see this combinatorial explosion as the number of nodes increases. All the different ways you can arrange those plus and minus signs on the edges while keeping the tree structure really contribute to this rapid growth.
It's starting to sound like a pretty fascinating combinatorial problem.
It really is.
Could you maybe walk us through an example to demonstrate how we reach those numbers? I'm thinking of the case with 4 nodes, A4 equals 10.
Sure, let's dive into that. So with 4 nodes, we've got 2 fundamental tree shapes to consider. First, we have the star shape, one central node connected to the other 3. Then you have the linear chain, where the nodes are connected in a sequence.
Okay, I can picture this.
Now, for the star shape, each of the 3 edges can be either positive or negative. So you have 2 possibilities for the first edge, 2 for the second, and 2 for the third, giving you a total of 2 times 2 equals 8 possibilities.
Right, so we're essentially accounting for all the possible combinations of pluses and minuses on the edges.
Exactly. Then for the linear chain, also with 4 nodes, we have 3 edges. But because of its linear structure, some of the sign combinations end up being equivalent. We have to be careful not to overcount due to those symmetries. So if we carefully analyze all the possibilities, we find that there are only 2 distinct ways to sign a linear chain with 4 nodes.
I see. So the shape of the tree, in addition to how those signs are arranged, is a key factor in determining the number of distinct signed trees.
Absolutely. As we increase the number of nodes, the interplay between the shape and the signs becomes even more complex. And that's what contributes to the fascinating patterns we see captured by this sequence.
Now, I know the OEIS entry for 80000000060 also mentions a formula and a generating function.
Right.
I'm sure our listeners are familiar with those. But maybe you could give a quick overview just for clarity, particularly the significance of the generating function in this context.
Sure. You can think of a generating function as a kind of a mathematical fingerprint for a specific integer sequence. It's basically taking the entire sequence and packing it into one neat function. It encodes all the properties and relationships of the sequence in a concise form. And what's particularly interesting about the generating function for A000006 is its connection to another sequence, A00000151. This sequence counts the number of rooted trees with a given number of nodes.
Oh, so there's a link between these 2 seemingly separate sequences.
Precisely. And by understanding this link, we can use the properties of one sequence to gain insights into the other. It's like building a bridge between 2 different mathematical landscapes.
Fascinating. And didn't the formula for A00000060 also connect to another sequence, A00000238, the one dealing with unrooted trees?
You're absolutely right. The formula for A000006 actually ties it to both A0000000051 and A00000238. It's amazing how interconnected everything is in the world of integer sequences.
It's like solving a giant puzzle where each sequence is a clue. And the formula is like the key that unlocks its secrets.
Well, we've definitely laid a solid foundation in this first part of our deep dive. We've looked at what signed trees are, the complexities of sequence A00000000, and how these sequences are all interconnected within the OEIS.
And in the next part, we can go deeper into the implications of these concepts, explore their connections to other areas of math, and even how they can be applied in fields beyond pure number theory. It's amazing how something that starts in pure math can have such far-reaching implications.
It really is. It's one of the things that makes mathematics so captivating, wouldn't you say?
Absolutely. It's like peeking behind the curtain of the universe and discovering that everything is connected in ways we never imagined.
As we continue this exploration of signed trees and these sequences, one can't help but wonder about the broader implications of all this. It may seem abstract, but often that's where the real beauty of number theory lies, in these unexpected connections to other fields.
Right, it's so intriguing how a concept from pure mathematics can have such far-reaching implications. Do you think exploring these connections is key to advancing our understanding, both theoretically and in terms of applications?
Absolutely. Take the connection between A00000606 and the sequences for rooted and unrooted trees, A00000151 and A000060. It's more than just a numerical relationship. It hints at a deeper structural similarity between these different types of trees.
A structural similarity. Could you maybe elaborate on that a bit? I'm sure our listeners are curious about how these tree concepts are related.
Sure. So with rooted trees, we pick a specific node and call it the root. This introduces a kind of hierarchy within the structure. Unrooted trees, on the other hand, lack that designated hierarchy. Now, the really fascinating thing is that by signing a tree, adding those positive and negative values to the edges, we can bridge the gap between these two concepts.
Wow, that's pretty insightful. So the act of signing a tree helps us understand the relationship between rooted and unrooted trees in a whole new way.
Precisely. By carefully analyzing the symmetries that emerge when we sign the edges, we can establish a correspondence between those different types of trees. It's like finding a secret passage that connects these seemingly separate mathematical worlds.
This interconnectedness is really fascinating. It's like we're uncovering this hidden network of relationships governing these abstract mathematical objects.
Exactly. And these relationships often extend beyond the realm of pure math and can provide insights into other scientific disciplines as well.
Earlier you mentioned potential applications in fields like computer science and physics.
Yeah.
Could you expand on how these seemingly abstract concepts might have real-world applications?
Certainly. Let's take computer science, for example. Trees are fundamental data structures used everywhere for organizing and manipulating data. Understanding the properties of signed trees, especially their combinatorial aspects, could lead to more efficient algorithms for searching and sorting data.
So the way we arrange information digitally could potentially be optimized by insights derived from the enumeration of signed trees.
Exactly. Think about it. By considering the balance and structure of signed trees, we might find completely new strategies for organizing data in a way that makes it faster to retrieve and manipulate. And that's just one example within computer science.
It's remarkable how a pure mathematical concept can connect to the world of digital information processing. Are there any other fields where we might see similar applications?
Oh, absolutely. Think about physics, for example. Networks are everywhere in physics. Networks of particles, networks of galaxies, even abstract networks like interacting spins in a magnetic material. And those positive and negative values representing signed edges, well, they can be used to model the interactions within these networks.
So you're saying that those same principles we use to analyze the structure of signed trees can be applied to understanding complex interactions in physical systems.
Exactly. By representing these systems as signed graphs, we can leverage the mathematical tools we've developed in graph theory and number theory to study their properties. For example, the stability of a magnetic material can be influenced by the balance of ferromagnetic and antiferromagnetic interactions between spins. And those can be represented as positive and negative edges in a signed graph.
Wow, it's amazing how a concept from abstract number theory can shed light on the behavior of physical materials.
It really is. And this interplay between theoretical and practical applications is what makes mathematics such a powerful tool for exploring the world around us. By delving into the abstract, we often end up uncovering these unexpected connections that illuminate the concrete.
I think this exploration of signed trees and their broader implications has really highlighted the interconnected nature of mathematical knowledge.
It has. And as we wrap up our deep dive in the next part, we'll touch on even more intriguing connections. particularly how these concepts relate to complex systems and the challenges they present to our understanding.
It's been quite a journey exploring the world of sign trees. We've gone from their definition and enumeration to their surprising connections with other mathematical concepts. And what's really striking is how these seemingly abstract ideas could help us understand complex systems in a variety of fields.
Definitely. As we've been discussing, the principles we've uncovered by looking at sign trees could apply to all sorts of networks, from those we find in computer science to the ones that govern the interactions of particles in physics. It really shows the power of abstract mathematical thinking.
And when we start thinking about complex systems, we encounter even more fascinating challenges, like biological networks, for example. Could this framework of sign trees offer any insight into that intricate web of interactions within living organisms?
That's a really interesting question. Biological networks are incredibly complex, with countless interacting components at multiple scales. While directly applying the concept of signed trees to something that intricate might be a stretch, the underlying principles of network analysis informed by what we know about signed graphs can give us valuable tools.
So while the specific structure of a sign tree might not directly map onto a biological network, the math tools we developed could still be helpful.
Exactly. Think about the concept of balance that we talked about earlier with signed trees. That idea of balance also has relevance when we're analyzing biological networks. In a biological system, having a balance between positive and negative interactions, kind of like those plus and minus signs in a sign graph, is often critical for maintaining stability and keeping things running smoothly.
That's a fascinating parallel. So those mathematical principles from sign trees, they give us a new way to look at the balance and organization of biological systems.
Precisely. By using those graph theory concepts, we can analyze those patterns of connectivity, pinpoint critical nodes or hubs, and understand how changes in one part of the network might ripple through and affect the whole system.
It really opens up a whole new way of exploring the complexity of life using a mathematical framework.
Absolutely. And it just goes to show how interconnected different scientific disciplines really are. The tools we create in one area, like studying sign trees and number theory, can have unexpected uses in fields as diverse as biology, physics, and computer science.
Well, as we wrap up this deep dive, it's clear that exploring abstract mathematical concepts like sign trees can lead to some really valuable and unexpected insights into the world around us. The connections we've seen between number theory, graph theory, and these complex systems are a testament to the power of math as a universal language for understanding the universe.
It really reminds us that exploring mathematical ideas out of pure curiosity can have profound implications for other scientific disciplines, leading to new discoveries and a deeper understanding of how knowledge is all interconnected.
Thank you for joining us on this journey through the world of sign trees and their amazing connections. We hope you're leaving with a sense of wonder and maybe a desire to delve even deeper into the fascinating world of mathematics and its power to illuminate our world.